Hi, this is a video, an AP Chemistry video, and we are going to be covering mainly, we're going to be covering covalent bond energies in this video. So just kind of to review with you, a chemical bond is a force of attraction between a group of atoms, and it makes them then behave as a unit. The bonds occur because there's a tendency for systems to seek the lowest possible energy. So being bonded together mostly results in lower energy, more stability than being unbonded atoms. So I'm not going to cover that, but I definitely go through these in the slide deck if you have time. But this is what I mainly want to focus in on are the bond energies. So this is in your textbook. This is just showing you the values of the bond energies for a variety of different covalent bonds. A couple things to notice here. If you, these are all positive values. So these are all the amount of energy in kilojoules to break 1 mole of this type of a bond. So they're in kilojoules per mole. But what I wanted to show you is also if you can see, like here's the nitrogen single bond, has a bond energy of 160 kilojoules per mole. You can also then see that the double bond and then the triple bond are here. So what's happening is as the bond goes from a single to a double to a triple, the bond energy increases. The size of the bonds, the distance between them, actually gets smaller. So as you go from a single to a double to a triple, the atoms are going to be closer together, which I think is covered in this one right here. So this is kind of showing you the single bond, the strength and length of what I'm talking about right now. So we are going to calculate the enthalpy changes that occur when bonds are formed and then when they're broken. When you form a bond, you end up with a system at lower energy. So overall, this is always an exothermic process for the most part. And when you're breaking bonds, energy has to be put in order to break the bond. So it's an endothermic process. So we're going to calculate delta H of the reaction by using those bond energies. So this is different than the sum of the products equals sum of the reactants, but yet you should get the same result. So let me just show you one. I think it'll make more sense once if you look at the equation here, what we're going to do is, remember the sigma is the sum of it's the sum of all the bonds that are broken, and N is, how many moles of those bonds. I'll show you that, an example of this. So we're going to sum up all the energies of the bonds that are required for the bonds to be broken. We're going to sum up all the energies of the bonds that are formed. We're going to keep everything positive, but then at the end, we're going to subtract because technically all of these are exothermic. So by subtracting, it makes those values negative. So here's an example of, hydrogen and fluorine reacting to form hydrogen fluoride. It's a gas. It's not an acid until you add it to water. But anyways, it is the sum of the bonds of the hydrogen and the fluorine minus 2 moles, because there's a 2 for the coefficient, times the bond energy of the HF bond. So if I look at my table, I'm looking for these values are directly from this table here. So overall, this is an exothermic process. So the energy that's put in to break the hydrogen and the fluorine bonds ends up being less than the energy that's released by the formation of the HF bonds. But let's try an example. So when you see an example like this, it's helpful to draw out the structures. If you don't want to draw them, you still have to kind of picture the bonds. So there's two of those. There's two fluorine-fluorine bonds. Notice these are just a really rough structure. It's not a true Lewis diagram, not the way that we draw them with lone pairs, but it does kind of help you, especially like with this molecule, to realize that there's two carbon-fluorine and two carbon-chlorine bonds. Then there's two hydrogen-fluorine bonds, and there's two hydrogen-chlorine bonds. So when I do these, I make kind of a T-chart, and I write down all of the bonds that have to be broken, and then all of the bonds that are formed. So the bonds that are broken are always going to be your reactants. Those have to be broken, and then they have to reform new bonds. Then the bonds that are formed are always going to be the products. So I am going to use the values from my bond energy chart. So if you're trying to do these problems, you might want to pause it or open this up in your textbook. You could, or open the slide deck so you have the numbers available. So here we go. So we have the carbon-hydrogen bond, and there's 4 of those. And then when I look that number up, it is 413 kilojoules per mole. And then there are the chlorine-chlorine. There's 2 of those, and each one of those chlorine-chlorine bonds is 239 kilojoules per mole. And then there's the fluorine bond, and there's 2 of those. So then I can just sum these up, and when I do, the energy required to break the bonds is going to be 2,438 kilojoules. So similarly, now I'm going to look at my products. So now I'm only using these. And I can see that I have the chlorine-fluorine bond. I have 2 of those. Carbon-fluorine. I have a carbon-chlorine bond. I have a hydrogen with fluorine bond. And I have a hydrogen with chlorine. Then I just look up those values. And then I sum them up. So this is how much energy is going to be released, essentially. But we're keeping everything positive at this point because we're going to then plug into the equation where we're going to take the energy of the bonds that were broken and then we're going to subtract the energy of the bonds that were formed. And by doing that, you are making all of those exothermic because energy is released. So all I need to do then is take my 2,438 kilojoules, subtract 3,632 kilojoules. And I don't have my calculator on me. So when I do this, you can tell it's going to be overall an exothermic process. So overall, the enthalpy of this reaction is negative 1,194 kilojoules. So let's try another one. And if you want to, these slides just go over the solution. This one here, I'll first of all, we'll kind of sketch them out so that you can picture the bonds, and then you could pause the video and try these on your own if you wanted. I got kind of a mess here. And I am going to try to add more space. So this one here, it is very important that you can draw these out so that you can understand what type of bonds are being broken. So the first one is going to look like this. And then plus the ozone, O3 is, you don't have to do like I said, I'm not going to put my lone pair electrons in there or anything. So those are my reactants, and then those are the bonds that'll have to be broken. The bonds that are going to be formed is, again, it's helpful to have this structure drawn out, or it'll be given to you, and then the O is double bonded to the O. So again, I'm going to figure out the amount of energy required to break these bonds, and I'm going to figure out the amount of energy essentially to that would be released when the bonds are formed, but I'm going to keep it positive, and then at the end I'm going to subtract those. So again, I would recommend that you do a T-chart, and I am going to do that with you. Broken first. So bonds that are broken, and then bonds that are formed. So you might now at this point want to pause the video and try this. And then just, you can definitely then unpause it and make sure that you're understanding. So we have a carbon-hydrogen bond in the first structure, and there's 4 of those. And those are 413 kilojoules per mole. There is also a double bond, sorry, can't talk. So a carbon-carbon double bond is going to be, and I didn't do this one ahead of time, so I have to look them up with you. 614. So there's one of these. So those are the bonds that are broken in the first structure. In the second structure, we have a double bond and a single bond between the oxygens. So the single bond between the oxygens is 146 kilojoules per mole, and the double bond is 495. So I can add all those up. I'm going to do that with you. Hopefully I don't make a mistake because I did not pre-work this problem. But anyways, so I get 2,907 kilojoules total, then the amount of energy required to break the bonds. So bonds formed, again, you really need to have that structure drawn out. There are those carbon-hydrogen bonds again, and there are 4 of them. I'll just point them out in case you don't see them. So there's 1, 2, 3, 4 of those. There is a carbon-carbon single bond, one of those, and the energy of a carbon-carbon is 347. So that just covered this bond. And now I'm going to do the carbon double bonded to the oxygen, which is 745. And there's one of those. And then lastly, I do need to address that oxygen. So there is the double bond oxygen. So there's one of those, and the energy is 495. So if I add those together, so I get the energy that's going to be released when the bonds are formed is going to be 3,239 kilojoules. So the enthalpy change of this reaction is going to be the energy to break the bonds minus the energy to form the bonds. So 2,907 minus 3,239, and I get negative 332 kilojoules. So overall, this, with all of those bonds that are broken and formed, this reaction is exothermic. I hope that helps. Let me know if you have any questions.